Welcome to the Unit 2, Section 1 video on relations and functions. Let's start this unit by talking about relating graphs to situations. Graphs can be used to illustrate many different situations. To relate a graph to a given situation, use keywords in the description. Be sure to read the graphs from left to right. This is important. You have to read the graphs from the left side to the right side. And this is going to become even more important later in this unit as we start to do domain and as we start to look at increasing and decreasing intervals and positive and negative intervals. You're going to be reading from left to right along the x-axis. So let's talk about the different types of situations we have. We have increasing graphs where the graph goes up, again, from left to right. Words that we use to describe increasing graphs include rose, gained, and grew. We also have decreasing graphs where the graph goes down from left to right. Words to describe this include fell, lessened, and diminished. Then we have constant graphs where the graph is flat. It is horizontal. And words we use to describe this are stays the same, steady, and continuous. You can divide the graph into sections every time the graph changes directions, then label each section. So here we have a picture on the left. We're going to use words to describe this graph on the right. So this graph, between each vertical dashed line, this graph first increases, then stays constant, increases again, and then finally decreases sharply. So you can see each of these four sections of the graph has a specific way of describing it. So let's do an example. For each, we're going to write if the height is rising, falling, or staying the same. So in A here, the height from left to right is going down, which means it's falling or decreasing. In B, we have a horizontal line, which means it's not changing, means it's staying the same or it's constant. And then for C, from left to right, we're going up or increasing, which means it is rising. For example 2, the air temperature was constant for several hours at the beginning of the day, and then rose steadily for several hours. It stayed the same temperature for most of the day before dropping sharply at sundown. We're going to choose the graph that best represents this situation. So we have graph A, graph B, and graph C. So let's pick out all the key words in this problem. First, we're going to read the graphs from left to right to show time passing, and then we're going to list the key words in order to decide which graph shows them. So let's list the key words here, starting with the first sentence. The air temperature was constant for several hours. Our key words here was constant, which means that the segment is horizontal. So we're going to look at our three graphs. Which of those three graphs starts out horizontal? Graph A does, graph B does, but graph C does not. Graph C starts out increasing. So we have narrowed our answers down to graphs A and B. The next part of the sentence says that it then rose steadily for several hours. So rose steadily is our key words, meaning that we're slanting upward or increasing. Well, graph A and graph B both slant upward or increase after we are horizontal. So we've got to move on to the next part. It stayed the same temperature for most of the day. So stayed the same is our key words. That means we're horizontal. So between graph A and graph B, which one is horizontal after it increases? Well, graph A is not because we're decreasing, but graph B is horizontal. So we have graph B, and then finally, we're dropping sharply at sundown. Drop sharply is the key word here. Segment description is slanting downward or decreasing, and that again is graph B. So let's take a look at graph B. We're going to pick the graph that shows all the key phrases in order. So if you look back at the problem, we're going to go piece by piece. We're horizontal, then we're slanting upward, then we're horizontal again, and then finally slanting downward. So the correct graph to describe the situation is graph B. Some graphs are connected lines or curves called continuous graphs. Continuous means the situation can include fractions or decimals. Some graphs are only distinct points. These are called discrete graphs. Discrete means the situation must have only specific amounts and usually consist of whole numbers only. So let's take a look at the difference between the two. A continuous graph is one like shown here, where we're looking at plant growth. We're looking at the height of the graph, or the height of the plant over time, okay? Height can include fractional amounts. You can see that the plant on its way to getting 5 inches tall by day 9, at some point before it was 5 inches, it had to be 4 inches. But it also had to be 4.5 inches. Also had to be 3 3/4 of an inch tall. It also had to be 1.5 inches tall on its way to being 5 inches tall, because it's going to pass those amounts on its way to where it ends up getting to. So this is a continuous graph. Examples of continuous graphs include time, temperature, and distance. An example of a discrete graph is shown here, where we have the remaining animals to adopt at an animal shelter. The number of animals is graphed over time. So on the first day, we have 8 animals left to adopt. Then on the second day, we have 7. We still have 7 on the third day, but then the number falls to 5 on the fourth day and continues to drop until we get down to 2 animals on the 7th day. Animals cannot be measured in fractional amounts. You cannot adopt out half of a cat or half of a dog. So in this case, points must be used to indicate how many animals we have at the end of each day. Examples of discrete variables are people, animals, and objects. Again, you cannot have half of a person or a fourth of a person. Same with animals and same with most objects. So in this example, Simon is selling candles to raise money for the school dance. For each candle he sells, the school will get $2.50. He has 10 candles that he can sell. We're going to sketch a graph of the situation and tell if it is continuous or discrete. So the amount earned is going to go on the y-axis, and it increases by $2.50 for each candle Simon sells. So here is a graph of it with all the points already plotted out. And each candle he sells, that's $2.50. So by the time he gets to 1 candle sold, he's made $2.50. If he sells 2, he's made $5, and so on and so forth. If he sells no candles, he makes no money. He cannot sell half of a candle to someone. So therefore, since he can only sell whole numbers of candles, because candles are objects, the graph is 11 distinct points. 10 for each candle that he can sell, plus 0 if he sells no candles at all. So that gives us our 11 points, and the graph is discrete. In this example, Angelique's heart rate is being monitored while she exercises on a treadmill. While walking, her heart rate remains the same. As she increases her pace, her heart rate rises at a steady rate. When she begins to run, her heart rate increases more rapidly, then remains high while she runs. As she decreases her pace, her heart rate slows down and returns to her normal rate. We're going to sketch the graph for this situation and tell if it is continuous or discrete. So as time passes during her workout, moving left to right along the x-axis, her heart rate, which is plotted on the y-axis, does the following. First, it remains the same, so we have a horizontal line over time. Then it rises at a steady rate, which is an increasing line over time. Then it increases more rapidly, so we're going to have a steeper increasing line. Then it remains high, so we're horizontal again before it slows down, so we're decreasing, and we return to our normal rate. So she levels out at her normal resting heart rate. So on the way to her heart rate getting higher, she passes all the heart rates in between. And so we have a line here instead of distinct points. So the graph is continuous. Now let's talk about writing situations for graphs. When sketching or interpreting a graph, pay close attention to the labels on each axis. Both graphs below show a relationship about a child going down a slide. Graph A represents the child's distance from the ground over time. So if you look at graph A, if he's going down a slide, he starts at a high distance from the ground, and then his distance from the ground goes down until he gets down to ground level, which is 0, over time. Graph B represents the child's speed over time. So as the child sits still at the top of the slide, the speed is 0. Then the speed goes up as he goes down the slide, and then as he levels out at the bottom of the slide, he starts to slow down until he stops. So you have to pay close attention to the labels on the axis to see what you are interpreting. Be sure to include a description of the x and y axis when you're writing situations for a graph, and whether the function is increasing, staying the same, or decreasing. You also need to include any change in the graph. So in example 5, we're going to write possible situation for the given graph. So here we have an increasing graph, then it stays constant, and then it decreases over time. And what's increasing and decreasing and staying the same is the water level. So first, we're going to identify the labels. The x-axis is time, and the y-axis is your water level. Then we're going to analyze the sections. So over time, the water level increases steadily, remains unchanged, then decreases steadily. So a possible situation for this graph is a watering can is filled with water. It sits for a while until some flowers are planted. The water is then emptied on top of the planted flowers. And if you match that situation to the graph, you'll see that it fits. Previously, you saw relationships represented by graphs. Relationships can also be represented by a set of ordered pairs called a relation. Relations are a way to relate a set of x values to a set of y values. For example, in the scoring system of some track meets, first place is worth 5 points, second place is worth 3 points, third place is worth 2 points, and fourth place is worth 1 point. This scoring system is a relation, so it can be shown as ordered pairs. So we're going to write the set of ordered pairs, and because it is a set, we're going to put it in curly braces. So first place is worth 5 points. So first place is 1, our x value, is worth 5 points, our y value. Second place is worth 3 points. So for second, we have 3 points, so our x and y values are as 2, 3. Third place is worth 2 points, so we have 3, 2. And fourth place is worth 1 point, so 4, 1. You can also show relations in other ways, such as tables, graphs, or mapping diagrams. So a table, in this situation, would essentially take your x value and your y value and put them side by side in each row of the table. So we have here, first place is worth 5 points, second is worth 3, third is worth 2, and 4 is worth 1. You can see each of our ordered pairs row by row. You're going to write all the x values under place and all the y values under points. For a graph, you can see our x values are on the x-axis, that is our place, and our y values are on the y-axis, which are our points. Okay, so use the x and y values of the ordered pairs to plot your graph. In a mapping diagram, we're going to put all of our place values on one side and all of our points on the other side. That's our x values and our y values. And then we're going to draw an arrow from the x value to the y value. So first place is worth 5 points. So we have 1 being arrowed to 5. 2 is being arrowed to 3. An arrow goes from 3 to 2, and an arrow goes from 4 to 1. In this example, let's express the relation shown by this set of ordered pairs, 1, 1, 2, 1, 4, 5, and 2, 6, as a table, graph, and mapping diagram. So for a table, we simply take each x value and write the y value that goes with it. So we have the x value 1 and the y value 1 from our first set of ordered pairs. Our second set of ordered pairs is 2, 1. Our third set is 4, 5. And our fourth set is 2, 6. Now you notice I swapped 4, 5, and 2, 6, mainly because it is good practice to write your x values in order. So we did 1, 2, 2, and 4, and we put the y values that go with them, 1, 1, 6, and 5. To do a graph, you simply take each set of ordered pairs and you plot them. And that would give you the graph that you see here. For a mapping diagram, we're going to write our x values in the first column, but you only have to write each x value one time. So since we have two x values that are 2, we're only going to write it one time. Same for the y values. We've got 1 being repeated, but we're only going to write it one time. Then we're going to draw our arrow. So we've got 1, 1, so we're going to draw an arrow from 1 to 1. We have 2, 1, so we're going to draw an arrow from 2 to 1. We have 4, 5, or rather, we've got 2, 6, so we're going to draw an arrow from 2 to 6. And then we have 4, 5, so we draw an arrow from 4 to 5. Let's wrap up this section by talking about identifying functions. A function is a special type of relation that pairs each x value with exactly one y value. No x values repeat. The y values can, however, repeat. In other words, the same y value can be paired with multiple x values. You just cannot have the same x value repeat. So in a function, your x value is referred to as your input. Then that input gets put into a function, and the result is your output, y. The x value represents the input for the function. The function is evaluated to produce an output represented by your y value. To determine if a set of ordered pairs is a function, you can use this flow diagram. So the first thing you want to ask is, are any input members the same? If none of the input members are the same, then you have a function. If you do have input members that are the same, then you have to ask this question. For any given input value, are any values for the output different? If no, then you have a function. If your answer to this question is yes, then it is not a function. So let's look at some examples of this. We're going to determine if the set of ordered pairs is a function. So here's our set of ordered pairs. We're first going to look at all the inputs. Every input value is different. So since every input value is different, we don't even have to look at the y values. We have a function. In the next example, again, we are going to look at the input values. In this case, we do have two input values that are the same. So now we have to look at the output values that go with it, or our y values. If our y values are different, such as we have here, then we do not have a function. In this set, again, we have two inputs or x values that are the same, but the y values that are with that same input are also the same. So since we essentially have the same point just written twice, then it is still a function because all the other x values are different. The same method is used to determine if a table represents a function, since it is simply another way to list a set of ordered pairs. So in this example, if we're going to determine if each relation represented is a function, we're going to first look at A here. Look at all your x values. We have -2, which repeats. So we look at the y values. One -2 has a 0, the other -2 has a 9. So since we have the same x value with different y values, it is not a function. For B, we look at all of our x values. Since all the x values are different, then it is a function. To determine if a mapping diagram represents a function, we're going to look at the arrows. If any one x value or input has multiple arrows leaving it, then it is not going to be a function. So we're going to determine a couple of examples here. Let's look at A. So we have our inputs being 1, 8, and 6. Look at 8. It's got 2 arrows going from it. So since 8 has 2 arrows going from it to 2 different y values, it is not a function. And if we look at B here, every x value has only 1 arrow leaving it. So since every x value has only 1 arrow leaving it, then it is a function. To determine if a graph represents a function, you're going to use the vertical line test. The vertical line test for a function states if any vertical line passes through no more than one point of the graph of a relation, then the relation is a function. So to do this, you can use your pencil. Place your pencil at the left of the graph to represent a vertical line. Slowly move the pencil to the right across the graph. For each value of x, this vertical line passes through no more than one point on the graph. This is true for every function. So we're going to look at a few graphs and we're going to determine if the graph is a function. So in A here, if you were to lay a pencil vertically and move it left to right across the graph, at x equals -3, you can see 1 point. All right, now follow the x-axis across. At -1, we have 1 point. At x equals 0, we have 1 point right at the origin. Keep going to the right. At x equals 2, we have only 1 point when you look up and down. At 3, look up and down, we only have 1 point again, and the same when we get to x equals 4. So at every x value, we have 1 point, so we have a function. For B, if we move left to right, at -4, x equals -4, we have 1 point when you look up and down. At x equals -3, we have 1 point when we look up and down. But when we get to x equals 1 and we look up and down, we have 2 points. So since there are 2 points, it is not a function. For C, if we were to lay a pencil vertically up and down, say in the middle of this graph, we're going to have a point going through that graph twice. So if we have a pencil laying, say, along the y-axis, look at the y-axis. That graph goes through y equals 4, and it goes through y equals -2 along the y-axis where x equals 0. So this is not a function. For D, if we pass a pencil from left to right, that line crosses the pencil no more than one time all the way through. So this is a function. At E, if we place a pencil and drag it from left to right, there are many places where we're going to have that line crossing our pencil twice. So it is not a function. And then at F, if we start our pencil from the left and go to the right, the line is only going to go through our pencil one time at any given point. So it is a function. Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you. And if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.